And welcome. Today we're going to talk about Green's theorem. So recall what we've been doing for the last few days has been work integrals over some curve going through two-dimensional space, and we have a vector field f, and we are going to follow some path r of t, and that is a way to compute work. So again, f is a vector field, and you can write it as p x comma y, q x comma y, and our path c is defined by r of t is equal to x of t, y of t. Okay, so we know now, we know also that we have several different ways to write this. We know that we can also write, if I take the derivative r prime, that's going to be x prime y prime. And another way to write that is dr is equal to r prime dt. And we write it like this. We write it going from a to b. So typically we think of the curve here is going from a to b of our function defined on our vector field defined on the actual path r, dotted with r prime, our velocity vector, dt. There are but other ways we also express this. There are so many different ways we've expressed this. Sometimes it gets a bit confusing. And this is just a recasting again. There is the tangent vector, and it's a unit vector. And we contain the length of, we talk about basically how much the dot product between the direction we're heading and the force field that we're working against times the small little length distance, and that clearly expresses the fact that this is a work that we're doing. So these are some of the ways we write down the line integral, and it turns out we're going to express one more. And each one of these ways, of course, expresses some nuance about the work integral. But we're going to do one more because it's going to be useful for us. So recall again that that dr is equal to r prime dt. So let's write that down. That is x prime y prime dt, and x prime is dx dt, dy dt, just like that, dt. We can think of the dt's as canceling, and we're left with only dx dy. Alright, so that's another way to express the same thing. So recall again that then f dot dr then can be written as, here's our f, so that's going to be p comma q, dotted with dx dy. All right, we do that dot product, and we get p dx plus q dy. All right, so now we have another way of expressing the same work integral or line integral through a vector field. We're going on the path c, and we're going to write it as p dx plus q dy. All right, so it turns out this representation exposes some nice structure about the line integral that we're going to exploit today when we talk about Green's theorem. Okay, so what is the statement of Green's theorem? So recall, we're going to have as a simple closed path. A simple closed path, so that it's just like that. So we start at some point, we end at the same point, and there's going to be no crossings, i.e. we're not going to do anything like this, and no double loops, no repeats. So we're not going to do this and then go around again. Okay. Another thing we want is that, so this is our C, all right, and then there's the region inside. We'll call this the D. So we're going to say that D then is the interior of C, and C contains only points in D, and that's another way of saying D has no holes. We also say that D is connected. So it's just a one piece. And we mean connected, we mean any point here and here inside the interior, we can always find a smooth path that's all in D that can connect the two. All right, so those are some of the little things we need to write down. So the actual expression of Green's theorem is this. We have this line integral, the work integral, and we have some vector field, and it's equal to, and here's the drum roll, the double integral of D over the partial with respect to Q of X minus the partial of P with respect to Y, dA. So so again, we can write this down as C P dx plus Q dy. All right, so this theorem, this formula, if you will, you're probably wondering, I would have never guessed that. You'd never guess that somehow is true, and you're trying to process what this means. All right, so let's put this in perspective, and we'll get a new sheet of paper out here. Okay, we'll write down the theorem again. Okay, we'll write down this theorem. There's the theorem again. So let's recall. So this is, I want to just say that this is analogous to the fundamental theorem of calculus. All right, so why is that true? So recall 1D functions. Like this, g prime of x, right? And we know we have an interval, and this interval, of course, is connected together, and it has some boundary. And the boundary now is going to be the point A and the point B, right? And so we have some function, g prime, that's defined on its interior. It's continuous. We can integrate it. We can do all that stuff. We can differentiate. All right. So what we have here then is we have this great relationship where the g at the value b minus g at the value a is equal to the integral from a to b of g prime of x dx. So I'd like to look at the parallels here. Here we have here as a 1D integral, and here you can think of this as these are zero-dimensional boundaries. So we can think of this as and what we're saying then is that knowledge about the integral of g prime is completely encapsulated in the value of g evaluated at the two boundary points on the edges of this set a comma b. And that's this really powerful result. We use it all the time in calculus and to do lots of things in physics. So now we have, again, the Green's theorem. We have a 2D integral here, where we have some function that's defined as such. And there's clearly derivatives in it, just like g prime here. But we can relate this area integral to an integral on the boundary. So recall again, we have some set D, and then we want to do this integral on that set of some function. I'm just going to call that function g of x comma y dA. We found out now, the statement of the theorem says if we look at the boundary of the set, which is that curve C going around it, that there's some relationship to an integral on the boundary. Like that. All right, so that might help you a little bit. So let's look at another point, another key fact there. So recall from the previous video we had, there was a theorem that f is conservative or otherwise we call it independent of path, if the partial of q with respect to x is equal to the partial of p with respect to y. So clearly in this case, if we make that a subtraction, let's say, just like what we see up here, and that's going to then be equal to 0. So clearly our g, in this case, x comma y, is going to be 0. And then the area integral over the region D that has no holes, like this, will be dA and will be equal to 0. And we know that that means that any closed path around that vector field is independent of path. So we verify exactly the statements we've seen before. So clearly this function is very important for helping us define independence of path. So this being 0, this difference between these two partial derivatives being 0, if it is so, then this integral over here becomes trivial, and we can easily calculate this very simple statement on a conservative vector field. But for any f, like perhaps could be non-conservative, this of course will not necessarily be true, and so this will be a non-zero quantity in there, and we'll have to integrate it. So this theorem of Green's theorem works for any vector field, provided our partial derivatives exist, provided that our set D that we're looking at has no holes, that f and all of these functions are integrable on that. All right, so that's just gives a little bit more structure as to what's going on with Green's theorem. So one thing we need to do, I think, is we can go and actually let's prove it. So we don't often do proofs in this class. But I think here is a good example of a thing, an opportunity to do something like this. So and we're going to do this on a rectangle. So this won't be the most general of proof. This will just give you an example of how to calculate this on a specific type of set. So let's write down what I mean. So we have our rectangle here. We're going from x equals a to b. And we're also going from y equals c all the way to d. Okay? And that's on the y-axis there. All right, so here's our rectangle. We'll call it D. And then what we want to do then is compute our line integral. So the convention here is always that our path going around our area will always be counterclockwise. Okay, and that's just the convention. If we did it clockwise, we just have to change the sign and everything. So that's no big deal. We just have to pick a convention. All right, so let's do that. So we can break this path then into, so C is the big path going all the way around, but we can break it into 4 little paths: C1, C2, C3, and C4. All right, and so the integral of f dr around the whole path is actually going to be the integral of C1 plus integral of C2 plus integral of C3 plus integral of C4. And I'll just put dots inside of there because we'll be putting that in every place. Okay? And that's going to be equal to the total work. All right, so let's set this up. But now we're going to use our form f dot dr we know is equal to p dx plus q dy. That was our new expression of the line integral. So we're going to use this to great effect here. So let's look at the first one. Let's look at just this path down here, C1 p dx. But notice that that because y is not changing, y is a constant value, it's only equal to c. There's no up or down on this line here. Because of that, this is why it's simpler to do on a rectangle. We can get rid of the dy. We know that dy here is equal to 0 because there's no up or down at all on this path C1. Right? So it becomes just p dx, and we can actually write that down as going from a to b of p x, and we evaluate y at c dx. Okay? While we're at it, why don't we add to it another integral, c3, right? So we'll do the c3 integral, and the same thing happens there. It's just p dx, and it's going to be a to b of p of x, comma d now, because y is equal to d up here, dx. So I'm going to add those together. So I'm adding this one and that one together. And I'm going to get, oh, sorry, one problem here. We're going from b to a, right? We're starting here at x equals b and going to a, right? So when I want to add these together, I want to change the integral around to make it only a to b, right? And that will make this a negative sign. So what we're going to do is we'll put a p of x comma c minus p of x comma d, right? Okay, and then dx. All right, so we've got, just like in the fundamental theorem of calculus, we see that our function p in y is evaluated at the boundaries, right? The boundary d, and here the boundary c. So I can rewrite this yet again as the integral a to b of the partial of p with respect to y, but we see it's a little backwards, so we have to put a minus sign there. And then we're going to take the integral from c to d, dy dx. Okay, so that looks good. The next thing we do is do the same argument for c2 and c4, and we'll note on these two parts of the path, dx is going to be equal to 0. So we're left with integral of c2 is going to be q dy, integral from c to d q. So we evaluate x at b, y, dy, and we're going to add to it the c4 integral, and that becomes from d to c of q evaluated at a for the x value, y, dy, and again, just like before, combine them together and create one integral. So it's going to go from c to d of q evaluated at b, comma y, minus q evaluated at a, comma y, dy. All right, now if you look at this, again, this looks like the difference of, if we ignore the y values here, we just look at those x's, it's clear that in terms of the x boundaries, these represent the boundaries of our x domain, and we're evaluated them at the difference. So this looks a lot like, again, a fundamental theorem of calculus type expression. So we go c to d, a to b, and we look, if this is the evaluated the boundaries, we know it must be the derivative on the interior. D, and now at this point it's dx dy. All right, now we're going to add together all of the paths together. So the work then is going to be equal to dr, the vector field times dr, or dot dr, and we're going to add this integral and that integral together. And of course, because all of these functions are smooth, we assume that they're continuous and all of that. We can switch the orders of integration on this integral or that integral, and we can get a to b, c to d of, we'll write that one there. It's going to be q, partial of q with respect to x. And again, there's a subtraction there, partial of p with respect to y. So I'm going to say that's just dy, dx, or rather the integral over the whole region times partial q of x, partial p of y dA. Right, so that is the proof, or more of a direct calculation of Green's theorem on a square. So obviously, if you have a strange shaped object, what we have to do then is I can put a square there. I can actually start tiling out our space and filling it out with a bunch of squares. And we know that because we're always going counterclockwise, if I have two abutting rectangles here, and I'm doing a path integral here, I'm going to be coming in and doing the path integral, and it's going to come down there. I'm always taking the convention of going counterclockwise. Likewise, here, I'm going to be going this way, and I'm going to be coming up, going the opposite direction. So where the two rectangles meet, we have a path integral piece, which we think of as C2, right? You're going to be going down in one direction and up in the other direction, which means that these two paths will cancel, and really you're going to be taking the path integral of the broader rectangle there, okay? Because those two will just go away. They'll cancel each other out. So what you'll end up is going all the way around this rectangle here. So if I do any subrectangles and I combine them together, automatically all these boundaries cancel out. So I can fill out my space like that, and so on and so forth. And that's one way to think about how we can prove this thing fully for any region, even non-smooth, even non-rectangular ones. So I won't get into the details of that proof. But that gives you an idea of why this is true. So this really is an expression of the fundamental theorem of calculus again, but we've now levered it up. We've leveraged it up to talk about not 1D integrals, but now 2D integrals. So let's use this to do some calculations. So recall in the previous lecture we talked about this force field. So let's do an example here. A force field that was really neat. We defined it as being 1 over r times the vector negative sine theta comma cosine theta. Okay, and we can also write this. We wrote this as negative y over x squared plus y squared, and x over x squared plus y squared. We wanted to establish before, is f conservative? But we had a problem that our set D had a hole. at the origin. We have the division by 0, right? So this vector field isn't defined at the origin. So because of that issue, it wasn't conservative on the entire plane, right? All right, and that means that if we took that, when we took that path r of t being the unit circle, and we're going from 0 to 2 pi, right? That when we took this, we did this work integral, it netted out to be 2 pi, which is definitely not 0, which indicated that we don't have an independence of path. So f is not conservative, right? Because of this issue. So, and the idea here is that we have the origin right there, and we have to sort of excise it from our set. And any path we choose around there, because as long as if the closed path encircles this point of where the function isn't defined, we get a non-zero path integral out of it. Okay, so that was the idea. But now let's talk about what happens when we have a path. So here's our Cartesian coordinates. There's our origin. What if I have I go out to 2, 2. And now I want to do a path, a unit circle that's now centered at 2, 2. What if I want to do that integral? All right. So what happens here? So recall again also, so this was our P and our Q, and we verified before that the partial of P with respect to Y, so I should say partial of Q with respect to X minus the partial of P with respect to Y is 0 for all points, but the point 0, 0. Provided that we were away from the origin, we had this nice result where the partials Q of X and P of Y, P with respect to Y, were equal. All right, so now on this set here, if I have this set here, this is going to be true. This is going to be a true statement, right? So the function is well defined everywhere here because we're away from the origin. We're going to cut out that origin. We're not going to consider it as part of our set. So we can actually write r of t is our. How do we write that? Well, we can do the same thing. We can actually just put a 2 there, plus cosine of t, and put a 2 there plus sine of t. So there's our path, and we can go r prime of t is going to be negative sine of t, cosine of t, just like before. All right. So now what we need to do is I want to compute this work integral on this set here, or on this new path centered away from the origin. So what I want to do is we have to evaluate. So I want to do this work integral. So we have to evaluate f on that place. So what we have to do is actually plug in. So that's the x of t value here, and that's the y of t value there. And we have to plug it into all these places up here. So let's look at p. P is going to be equal to negative y, so that'll be a negative 2 minus sine t over, and now we have to take both of these squared, so that becomes a 2 plus cosine t quantity squared plus 2 sine plus sine t quantity squared. So this is looking pretty ugly, and we could keep going like this, and what we're going to get for an expression f dot dr is going to be big and complex. I'm not saying you can't do it, but it would definitely be hard. So we've hit a wall here with computing any closed path, with computing this pretty simple closed path that doesn't go around the origin. So this is a very onerous thing. So our line integral is very difficult to compute. But let's try using Green's theorem. Okay. So let's do the same thing. So our set D then is going to be the circle. The circle at, I should say the circle at 2, 2, centered at 2, 2, radius 1. Okay, so that's our circle. And now we can write this. We know that the work integral of our along the boundary of that circle of our function, our vector field f dr. But now we can write out the Green's theorem version of it. The interior of that circle has to be equal to partial of q with respect to x minus partial of p with respect to y dA. Alright, so what was q again? Q was equal to negative y over x squared plus y squared, and p was equal to x over x squared plus y squared. And I've already indicated this was equal to 0, right? So now, of course, our integral, we've proven already then that if the integrand over that whole region is 0, then the integral will be 0 as well. So now we have a nice statement. We have a nice statement about the work, that it's always going to be 0. So and this works for any circle, any closed path, I should say. Closed path not including the origin. All right, so this is again a neat result. Again, any path that contains the origin, the work is going to be non-zero. But for any path away from the origin, the work is going to always be 0. So here's a really neat, really neat result. So again, because there's this hole in our space, we have to sort of pull it out. Any path that's tied around the origin, we can't really move it off. We can't continuously move that path off over that 0, that origin point. As the line, if I were to try to pull this path off continuously, kind of like, think of it as like a lasso. If I'm going to try to pull my lasso off from this point 0, 0, I can't. It's like a pole that our rope is tied to. So if I try to bring that in, the minute it gets, the minute I pull that lasso and it goes right over the top of the origin, there's a point where our vector field is not defined. It's infinite at that point, and so our integral won't be defined, and so we're going to have problems. So we have this nice dichotomy here. We've used Green's theorem now to prove that this path here, this work integral, can be done really simply by just taking the partials, which in this case were 0. So we can use that, of course, in other examples to calculate work integrals by doing an area integral instead. And sometimes the area integral, of course, will be a lot easier to do than the path integral. All right, so thank you very much.